So coming to the second part of the video, now we'll check out the simulation. So now you can just see this is geometry what I have taken. So this part is the anode and this part is the cathode. So cathode has this shape. I think you can see the cathode, right? So then this will be our cathode wall onto which, so this part, so combined with these three surfaces is the cathode wall onto which the chromium alloy or chromium metal will be deposited. So I'm taking potassium chromate solution or potassium dichromate solution. So they are Cr2O72 minus ions which are present in the electrolyte solution. So that will overcome the barrier of the Gibbs free energy and it will deposit onto the cathode, right? So now, and this is the solution, electrolyte solution, and this is the anode wall. So now I have named these sections. One is cathode wall, which is three surfaces, anode wall, which is inside surface, and the container walls. The container walls will not have any electrical current density or anything. It is zero. Okay, so now I will try to mesh it. Just double click on the mesh. So I'll just close this part. I'm just using a normal mesh or a simple mesh for only demonstration purpose. So if you want to have a good quality mesh, you can refine it, as well as in order to capture properly the thickness onto the container wall also you need to refine the mesh near the wall. I'm going to just take a normal mesh here. So once it's being loaded, it's taking some time. Yeah, it's got loaded. The mesh. Just click on the mesh and I'll be using the 0.05 as the sizing, and I'll do generate mesh. I think this mesh is sufficient for us only for demonstration purpose. I'll just close this. Now right click, update it. So here we are bothered about the cathode plate onto which the chromium ions will be deposited or a chromium metal will be deposited according to the shape of the cathode. So depending on the shape of the cathode and the anode, the amount that is being deposited will vary. So you need to take that variation of the shape also into consideration. But obviously, depending on the shape of the anode and shape of the cathode, the deposition content will also change. So I'm just switched on the fluid. Here we will do the transient simulation because the deposition varies with respect to time. Go to general, click on transient. Here we really don't bother about the energy properties because we are taking a constant this one constant temperature. I just change it to laminar. It doesn't matter because we are not really bothered about the flow here. Go to species transport and volumetric and electrochemical. Click on OK. Now we need to create our own material. So maybe before getting into that material, I'll try to import what are all the conditions that have been required. I'll just click on this, and in the names I'll be going so we need to have fluid database. So fluids, I need to have oxygen. Click on the oxygen. O2. Scroll down. Just okay. Anyways, I'll just search that S2 liquid also is required. Copy and H plus hydrogen is required. Yeah, oxygen, here we got it, oxygen, copy, and hydrogen, helium, select for hydrogen ion, I think it's missed somewhere to check hydrogen ion, CH plus, plus, sorry, here it is, copy, close, and we need to create other two one also. One is dichromate ion Cr2O7 2 minus. Those will be not available ready made in the window. Cr2O7 2 minus. Cr2O7 2 minus. Right, and density will take a constant density 2680. Specific heat it's 186. And standard state enthalpy 20799 and entropy 6610. Chain create. No, this will be sufficient. Now again sorry, just rename this. Now it is chromium Cr. Again you can select Cr. The chromium density is 7150. Specific heat 448 and molecular weight is 51.99384. Standard enthalpy is 0 and entropy is 18866.4. Change create. No. Forgot to change dichromate ion molecular weight. Dichromate ion molecular weight is 215.9878. Okay. Now we need to mention the reactions. So go to edit, go to the names section. So chromium is a solid species. Add here. We don't want nitrogen. Remove. We want atomic hydrogen. And this. Add it, and add this one. Right. We don't want water or vapor also. So this is 4 and this is chromium. So now we'll go to finite rate and we'll try to mention the number of reactions. Reactants are 2 here. Number of products are 2. So Cr2O7 with the stoichiometric coefficient as 1 and H plus 14. There is no rate exponent for this, and here it is a electrochemical, so we'll go for chromium and H2O. Chromium coefficient is 2, this is 7. And this is the anode transfer coefficient what we have mentioned here, that is alpha, and this is a cathode transfer coefficient, that is other alpha. You can just see on the screen. So these are the alphas what I mentioned, anode transfer coefficient and cathode transfer coefficients. So both are 0.5, 0.5, and electric charge density, this will take it as a value as, I mean, at the exchange density, that is, this is the charge that is required, current density in order to overcome that, and equilibrium potential is 1.23. Sorry, 0.4, can take this. These are the values, depends on the amount of barrier and amount of the values what you need to mention there. So it all depends on your experimentation setup or your chromium metal deposition and the properties of the, sorry, we need to mention here two reactions. So there was one reaction, we'll go to for the second reaction. Here also we'll mention two reactants and two products. It's sorry, it's one reactant, two products. This is H2O liquid. Stoichiometric quotient as 1 and rate exponent as 1, and two species, H plus and O2. This is 1 and this is 4. Right. And here, so this is the same coefficients. Exchange current density is here we are taking it as 100, which is required the current density that to overcome the barrier. And for the equilibrium potential is 1.43. Sorry, 1.23. This is the equilibrium potential when it is in equilibrium, as I have mentioned in the previous track, where the Gibbs free energy for the forward anodic and the forward backward cathodic, so both are same, then there is the equilibrium. So this equilibrium will not exist in reality. In reality, this is the actual process where there will be a higher anode or a higher cathode Gibbs free energy that need to be overcome in order for the reaction to be take place, or the deposition of the metal to be taken place. Right, so click on OK. So now you can see, so this is the first and this is the second. Sorry, there are two reactants. The first one, oh sorry, I misplaced the did not consider the second one. So okay, we can take consider this as the first reactant, and in the second change this again to ID2, and here we will say chromium with H plus 14, rate exponent as 0, this rate exponent as 0, water liquid and the Cr. So this is the best balancing of the chemical reactions. Okay, yeah. And the density we'll take it as an volume weighted mixing law, and the viscosity we'll take 0.0001, and the little conductivity I'll take it as 50. It's a overall for the entire mixture. And then the reaction mechanisms. So we need to mention the charge densities properly. We have not mentioned in the materials, so that's the reason when these errors are coming. Just go to Cr272 minus, which is -2. Change create, and for atomic control it is +1. Change create. So that should be sufficient. And now go to this one, and so volume weighted mixing law, change, close, apply. Okay, and you also need to mention the mechanism 1 and 2. So go to edit. So this is an electrochemical mechanism 1. Next, this is electrochemical mechanism 2. So there should be two mechanisms. Number of mechanisms are, just unselect this, number of two mechanisms. This is mechanism ID 1. For this, click OK. Okay. And for this, mechanism 1. This is mechanism ID 2. Just cross verify once. This is for 1. So in the boundary conditions, just go and verify at the cathode wall second mechanism should be present. Potential, electrochemical. So this is the second mechanism, and in the specified flux of current density, I am taking the value of 20490 sorry 24090.1 ampere per meter square. So this is a specified flux, and in the species you can just leave default, apply. Close. But in the species, if you want to mention the amount of H plus or anything, you just can mention. Maybe I'll mention just 0.2 of this fraction, and the water vapor liquid is 0.1, and oxygen is maybe 0.1. It all depends on how much is the concentration that you want to mention, right? And also the anode wall you can just select. Similarly, mention whatever fraction you find it relevant. And this potential we can take specified value of current potential, that is 0, and here is the mechanism 1 that will happen. Apply, close, and now verify what are the mechanisms you have taken once. I have doubt that whether I have taken it properly or not. Number of mechanisms 2. In this mechanism ID, it's 2 mechanism ID. Okay. And this mechanism ID 1. Okay. Let's check. Okay, it's going to 2, it's going to 1. Yes, this is okay. Change, close, apply. Okay, now try to initialize. Use certain fractions, whatever fractions you require. Initialize and try to run calculation and mention number of time steps will be 500, and I'll take the time step size as 0.01 and calculate. So there is an issue here, so I will just debug that. We need so I've modified the things. The charge number should be given here. So this is 1 here, and the dichromate ion is -2. So now that is okay. Now it is running for, it will run fine. So I'll just initialize and just try to run the calculation. It's running good. So that is the charge numbers we need to give in the mixture properties. I have given in the fluid individual properties.
ఈ చంద్రరావు గారు తిక్కులోడు నీతి నిజాయితీ అంటూ ఎప్పుడు ఏదో చెత్తంతా వాడుతూ ఉంటాడు. కానీ ఈ రోజు మాత్రం వాయిస్ ప్లానింగ్
So, so I need to allow it run for 1.3 seconds. That will be sufficient. So and we need to, if you want to have the deposited mass onto the cathode, so there is a simple formula that we need to implement. So that is Q by F into M by Z, where Z is the valence of the number of electrons that is present on the outer orbit of the chromium, that is 6, and this is the M, which is the molecular mass gram per mole. F is the Faraday's constant, and Q is the charge, which is the amount of current density, that is ampere per meter square, into the surface area that you need to multiply in order to get I, right? So I is the current magnitude into surface area into the time that is being calculated, that is a flow time. So with respect to time, what is the amount of charge that is being going and deposited? This gives the mass that is being deposited onto the cathode. So I just created a custom field function for the deposition. I'll just show it to you. What is that function? This is the function flow time into the area and the current density, which is ampere per meter square. So this area into ampere per meter square gives the ampere into, this is the molecular weight of chromium, divided by 6, which is valence electrons of chromium, divided by the Faraday's constant. So we can just go to the graphics and I'll just show you the counter of the deposition. You can just check. So this is the deposition that has been happening onto the cathode, so which is least here and highest here, because it is in line with the anode. Anode is present just center of this. That's the reason why there is more amount of chromium deposition that is happening, which is in line with anode. But if it is away from the anode, this is happening the least, right? So this is the deposition rate, and you can also check different other current magnitude also. You can just select these walls and check the current magnitude. So depending on the current magnitude, obviously there will be more deposition, and you can just select the potentials, how it is been getting varied with respect to the surface. And you can check the heat sources. Of course, we are not solving any temperature, so it will not show any heat sources. And you can also check for the species fractions. These are constant boundary conditions, so you need to create a plane. So in order to verify that, I've created a plane here, right? So we can modify that stuff in order to check how exactly these are getting varied, right? Similarly, if you want to check the proportions of this liquid also, water liquid, where it is exactly forming, how it is varying. So all this stuff you can just vary the chromium ion deposition or variability where it is higher, lower. Everything can be seen from the species equations, and you can just check for these pressures. Maybe it will not vary that much. It only depends on the height. Yes. So this is the way how you can calculate the deposited mass onto the your electrodes, which is called electroplating. So I hope this made a sense to you guys, and in order to perform a simulation of how running an electroplating simulation in ANSYS Fluid, please do subscribe the channel and share among your friends group if you find it is more relevant to them. Thank you.